So for number 3 on worksheet 8, we want to prove that it has to be the case that there are exactly the same number of even permutations as there are odd permutations in H. So we are going to assume that H is a subset of Sn and that there exists an odd element in H. So what we're saying there is basically that the H is not only even elements. Also, it's impossible for H to be only odd permutations because E is an element of H and E is even. So H containing only odd permutations is impossible, and H containing only even permutations does not apply here. So we're just looking at the case where there are both even and odd. So we're assuming that there's at least one odd permutation in H. And we're calling that, oh, I forgot what that symbol is called. I think it's sigma. Let's go with sigma. So AN is the set of even permutations on H. H minus a to the n is going to be the set of odd permutations. So that's just the notation in the proof. So for any odd permutation, beta, that's an element of H, we know that sigma times beta is an element of H is going to be even because the product of two odd permutations is even. So our permutation is odd because we picked it that way. So for any other odd permutation in H, an odd permutation times an odd permutation is even. So this implies that the total number of odd permutations has to be less than or equal to the number of even permutations in H. Similarly, if we take an even permutation in H, I called it beta prime, then sigma times beta prime, which is an element of H, is also odd. And that implies the total number of even permutations has to be less than or equal to the total number of odd. If you put these together, it implies that the number of even permutations has to be equal to the